Hello, my name is Scalet, and I'm presenting here our work on a subpolynomial-time algorithm for the free energy of one-dimensional quantum systems in the thermodynamic limit. This is joint work with Hamza and Omar Fawzi, and you can find the full version of our work on the archive. Let me also thank the organizers of ITCS 2023 for giving us the opportunity to present our work here. I'll start with introducing the setup of our problem. We're interested in multipartite quantum systems. So you can think of like atoms aligned on a chain, and each of these atoms has some degree of freedom, for example, by an electron, which has a spin degree of freedom or something like that. We model each of these local systems by a d-dimensional Hilbert space, and thereby the whole system as a tensor product of these local Hilbert spaces, which is then a multipartite Hilbert space of dimension d to the n, where n is the number of particles that we have in our chain. We will later on take this number of particles to infinity, so will actually not come up in these calculations later on. Also, we assume this is actually how we use the geometry of this chain, that interactions are just local, so there will just be nearest neighbor interactions between two neighboring particles. Think of something like an energy penalty term for spins that are not aligned in a ferromagnet, something like that. As we assume our system to be translation invariant, we will only have one of these interactions, which is then repeated on each pair of neighboring sides. This interaction term is given by a complex Hermitian matrix H, which is then a d squared times d squared matrix, because it acts on two sides. The Hamiltonian of the whole system on n sides is then given by a sum of all these neighboring interaction terms. So you sum up the first and second and third interaction, and so on, and you obtain a d to the n times d to the n matrix. Each of these terms is basically also d to the n times d to the n matrix, but acting trivially on a number of sides, then acting on two sides, and then acting as the identity again on the remaining sides. As these terms are just always acting on two sides, the whole matrix is actually sparse. The quantity we are interested in is the free energy. It's given by the following formula. You first compute the exponential of the Hamiltonian that we just mentioned times the inverse temperature, beta is the inverse temperature, and take a trace of that. This trace of the exponential is also called the partition function z. Afterwards, take a logarithm, multiply by temperature, and normalize by the system size. The system size, as we said beforehand, will be taken to infinity, which is the thermodynamic limit. I mentioned beforehand that the matrix H is sparse, but the exponential of a sparse matrix is no longer necessarily sparse. So it's not efficient to just compute this in n, because the size of this matrix will grow exponentially with n, and that's basically what determines the computational time you need to compute this quantity here, if you do it straightforwardly by just linear algebra computations. I also want to introduce the thermal state, which is the state that describes the system. If you have a physical system at a certain given temperature, 1 over beta, it's basically also this exponential again, times the normalization factor. The reason why we're interested in the free energy is that it gives access to thermodynamic observables. These are basically, you take some Hermitian operators acting on a side times the thermal state and the trace of it. This gives you the expectation value of the observable O. So any physical quantities like energy, magnetization, heat capacity is not in this form, but you can also derive it from other observables. So you can compute all these quantities either by having access to the thermal state, but also directly by taking some derivatives of this function f beta of h with respect to parameters you have to introduce. Basically, adding the observable to the parameter h and taking the derivative with respect to this gives you access to thermodynamic observables. So if you're able to compute f, you're able to compute basically anything you not want to know physically about this system in its thermal state. Also, not as relevant in our work, but in general, the free energy sometimes has non-analyticities, and these are called phase transitions and are also physically interesting. This way of introducing the free energy as a log partition function is a bit more combinatorial. An alternative formula is given as follows. You can instead, again, define the free energy as a limit of the system size going to infinity and normalize by the system size. So actually the free energy density. And for each system size, you minimize this functional, which is for a given physical state, gives you the energy of the state minus the entropy times the temperature. So for low temperatures, high beta, you basically just minimize the energy. And for increasing temperatures, you will try to maximize the entropy of the system. The minimization is you're taking over all states which are positive semi-definite matrices which are normalized. The minimizer of this formula can be easily figured out is just the thermal state introduced in the previous slide. And as I just said, if you take the limit beta to infinity, you actually obtain the ground state energy, which is a related problem to the free energy. This is also interesting because the ground state problem is known to be QMAX hard to compute, so not even by a quantum computer. You expect to be in general be able to compute the ground state energy. This has been proven by Gottesman and Urani. And this actually means when we look at algorithms to compute the free energy, whatever we do, these algorithms will not be expected to be efficient in the beta, because if they were, you could just use them to just compute the free energy for a high beta and thereby compute approximate the ground state energy. So we will not expect to be efficient in beta in particular, as long as these two complexity classes, QMA exp and exp, are not the same. It is not possible to get a polynomial runtime in beta for free energy approximation. So with this in mind, we are able to look at the main result of our work, which is an algorithm to compute the free energy at a fixed temperature. The algorithm takes as input this interaction matrix, described by this CD squared times D squared matrix. And these interaction matrices are assumed to be norm no bigger than 1, otherwise you could just include the beta dependency in the H. Furthermore, what we take as the actual input of the algorithm is the accuracy that we want to achieve with the algorithm, so some number greater 0. And the actually interesting thing, as we have no system size and there's just one matrix describing the interaction, the actually interesting thing is how does the complexity of the algorithm scale with this accuracy we want to achieve. The output of the algorithm is then obviously estimation and approximation of the free energy up to accuracy epsilon. And the runtime is then given by this a bit bulky expression, an exponential in the logarithm of 1 over epsilon divided by log 1 over epsilon. What you can see is this factor here improves slightly upon a just polynomial runtime in 1 over epsilon. So that's why we have a subpolynomial runtime in the inverse error. This is also the improvement compared to the best previous work for computing the free energy, which is a runtime which is polynomial in 1 over epsilon, where C is just some fixed constant, even growing quite quickly with the inverse temperature. This is a work from Kuwahara and Saito. An additional advantage of our algorithm is that it's quite simple to implement. We will look at the actual algorithm a bit later, where we can see it's just a very simple linear algebra computation for certain linear maps that you have to write down, which we will consider later. Also, as already mentioned, this only holds at fixed temperature, and if you would write down this runtime, including the beta dependent, we would find that it's doubly exponential in beta. But as we said, we don't expect an efficient algorithm in beta because it would solve the computationally hard ground state problem. Furthermore, in the introduction, I mentioned how you can compute thermal expectation values and just using the free energy. You could do this by just using this algorithm in a black box way, but it will turn out actually the algorithm gives as a side result just an immediate description of marginals of the thermal state, which you can then directly use to compute like thermal expectation values and other things. Also, as I just mentioned, as our algorithm is quite simple to implement, we also did this and tried it out on a toy Hamiltonian. Here's the XY Hamiltonian. And the interesting thing about the XY Hamiltonian for us was basically just that it's has an analytic solution, so we could actually just obtain an analytic expression for the thermal expectation values and free energy in the thermodynamic limit directly, and compared to those for showing how well our algorithm works. Thereby, these error rates that you can see here in these graphs are actually computed compared to the analytic solution. They're not the error bounds we get from our proof, which would be a bit worse. What you can see is also actually in practice, it works quite well for example, for the fairly high temperatures, but not too high temperatures, you get down to machine precision in the computation of the free energy. All these data points, basically L here describes more or less the runtime of the algorithm, but even for the largest runtimes, it just took a few seconds to compute each data point. Also, the error actually at some point can drop to 0, because we don't know whether our algorithm gives a lower or upper bound. So it just happens at some point, possibly, that the error crosses 0. Also here you can see this, as mentioned, this parameter L basically describes the runtime. The runtime will scale exponentially with L. And you can see here how the error decreases with this parameter describing the runtime. To get an idea of how we prove this result, we first look at the classical case, which is actually considerably simpler, but it still gives some intuition of how the quantum case works as well. When I say classical case, what I mean is this interaction matrix is diagonal. So instead of describing this complex Hermitian matrix, we just look at these values on the diagonal. These are just real numbers here, describing the energy that you have for any sort of neighboring configuration. So this number H11 is if two neighboring sites are both in state 1 and up to state D, we describe all these interaction energies. This replaces the formula with a trace of the exponential of these Hamiltonians. By this formula, here we just look at the petition function, the logarithm of it times some factor, what gives the free energy. And what you have this sum, this exponential of sum over numbers. Instead of a trace, you just sum over all possible configurations of the system. This means, as opposed to the quantum case, these are just commuting terms. And you can just take this exponential apart and treat all these terms separately. This also means the summation always just applies to 2 of these terms. In particular, if you consider each of these terms to be a matrix in the indices J1 and J2, then you just have to sum over these indices to make a matrix multiplication. So all this calculation is just a different way of writing out a matrix multiplication. And the last sum would here be a trace then. We call this matrix T here the transfer matrix. This is actually, this whole computation is a well-known trick called the technique of transfer matrices in statistical mechanics. And if you look what this computation actually turns out to be, you basically just have to sum over all eigenvalues of the matrix T to the power of n. If you then do actually the thermodynamic limit, so you take the system size to infinity and take the logarithm of this quantity, the only eigenvalue that contributes is the spectral radius. So in fact, the whole computation of the partition function in classical case is just take this transfer matrix, write it down, compute its spectral radius, and then you're basically done and have computed the free energy up to some logarithm and normalization factor. The even more convenient thing is this largest eigenvalue will be equal to the spectral radius by the Frobenius theory. That is because the transfer matrix only has positive entries, because these were all these exponentials of some real numbers. As I said, then you just do a small computation. This is -1 over beta logarithm of the maximal eigenvalue of this matrix to get the free energy. And you can also obtain the marginals of the thermal state in this computation. Here, to the maximal eigenvalue, you have a corresponding eigenvector, and the entries of this eigenvectors are basically the probability distribution of a one-side margin of the thermal state. If you want to have several sides of this marginal, you can just multiply by the transfer matrix to obtain these as well. So you can also compute several side thermal expectation values easily. This all works because classical thermal states are Markov networks, or in 1D Markov chains. This is by the Hamilton-Clifford theorem that, these Gibbs states of thermal states are just equivalent to Markov networks or Markov chains in 1D. So with this motivation in mind, let's now have a look at the quantum case. So quantum case is a lot different. For example, this Markov property I just mentioned does no longer hold in the quantum case. You will have something similar called an approximate quantum Markov property, but it would be much harder to use immediately for this computation. And also, this was mentioned in the introduction, as we have the free energy for classical systems basically computed independently of beta, you can also get the ground state energy of classical systems easily. But we actually know, on the other hand, that in the quantum case, the ground state problem is QMAX hard. So the whole complexity of the quantum system is way more difficult than in the classical case. Still, we take some inspiration from this classical case and try to write something down similar to the transfer matrix in the classical case, which turns out to be a lot more complicated object. which is given here. What you have a matrix multiplication where you take an input state, multiply things that look a bit like thermal states or inverses of thermal states from both sides, and then shift the system by one side. This is what we call the non-commutative transfer matrix, and it has been introduced by Araki in 1969 already. What he used it for was to prove the analyticity of the free energy, and thereby the absence of phase transitions in 1D. What he actually considers is not only this map, but he takes a limit of this number L going to infinity. As you can see, with the number L, these matrix sizes grow. So actually, this limit is a map from an infinite dimensional space to an infinite dimensional space, and would not actually help us with computing spectral radii or writing down an actual algorithm. Nevertheless, in this limit and with a certain notion of C-star algebras and states on C-star algebras, he could prove that eigenvalue and eigenvectors of this map correspond to free energy and thermal state, but just if you take the limit of this map. So the idea for us is then, what can we do if we just consider finite dimensional maps, in particular this maps written down here? Do their spectral radii converge to the spectral radius of the limit map? And also, what about the corresponding eigenvectors then? The technical tool we use for that is also taken from Araki. It's basically these factors here, which correspond to, again, let's consider the classical case. You take something like the thermal state, and then basically it's inverse, but on one side less. In the classical case, where these matrices commute, this would just cancel, and you basically recover the classical transfer matrix. In the quantum case, this is no longer true, but still, if you take this parameter to infinity, Araki proved that these factors, these matrix products, will converge to something. What we now want to do is we want to use these convergence results and prove something about the eigenvalues and eigenvectors of this matrix, of this linear map. And we do this by considering an ansatz for an approximate eigenvector of this map. It should be mentioned that it's not straightforward to use standard perturbation theory, firstly because this map changes dimension with the parameter L, and also because it's non-Hermitian, which is what most perturbation bounds for eigenvalues would work for. The ansatz for an approximate eigenvector that we use is just the thermal state, or the marginal of the thermal state on L sides, and that we plug into this formula. This helps us to use a variational expression for the spectral radius, the so-called Collatz-Wieland formula, to give estimates on the spectral radius. Given that the convergence rate proven in Araki for this factor is super exponentially fast, we were able to also prove super exponential convergence of the spectral radius of this L star L map to the true free energy, or rather exponential of minus beta times the true free energy. The super exponential convergence versus just exponential convergence is actually what gives us improvement in our algorithm from polynomial time to subpolynomial time. The next thing, despite the eigenvalue, is also the eigenvector. This again has an additional problem, namely just having the convergence of the spectral radius does not immediately give you the convergence of the corresponding eigenvector. In addition, you need something called a primitivity condition. This means that the map L star L maps all positive semi-definite operators to positive definite operators. In addition, we want this in a quantitative version, so we just not only want that it's positive definite, but we also want to lower bound its minimum eigenvalue. This will actually decay exponentially with the number L, but still we need some bound on the decay rate, and also we need a bound from what L actually this works. When we have a quantitative primitivity condition, we can use something called Perot-Frobenius theory for positive operators, as opposed to the one for just matrices with positive entries, to prove the convergence of this eigenvector, which involves also technical tools like the Hilbert's projective metric in our proof. This then proves that if you do this spectral radius calculation and just compute the corresponding eigenvector, you immediately get the thermal state. I mentioned in the introduction you would not actually need this, because you can just use the computation of the free energy in a black box way, compute its derivatives to get thermal expectation values, and thereby actually also marginals of the thermal state. But it turns out to be way more convenient to just immediately get this thermal state as a byproduct. And it also turns out in practice, it's a lot more efficient to compute correlation functions, because if you want to compute correlation functions using derivatives, you would first have to block the system up to the size of the correlation function you want to compute, and only then use this derivative method, which makes the computation way more expensive. So it's quite convenient to immediately get a thermal state on several sides out of the algorithm we present. With this, I'm also already about to conclude my talk. What we did in this work is we present an algorithm to compute the free energy, in the particular case of translation invariant 1D quantum systems in the thermodynamic limit. And we use proof techniques that also treats these types of systems and proves the analyticity of free energy in one dimension. This is work from Araki, and the quantities and maps coming up in this work also allow us to present an algorithm based on these. It turns out that our algorithm is also particularly simple to implement and gives quite precise results in practice if you use it for 1D quantum systems. Also, I've put down a table here which kind of gives us a bigger picture of how this algorithmic efficiency fits into different settings. I mentioned already in the beginning that we have a ground state problem, which is computationally hard already in one dimension for this specific setting of translation invariant 1D quantum systems. Given that this already holds in 1D, that it's computationally hard to compute or approximate the ground state energy, and this also extends to higher dimension directly. This is not true for the classic case. This is just true in the quantum case. Conversely, as long as you take any finite temperature, but you don't consider the runtime with temperature, just you fix the temperature and consider the runtime with the inverse error you want to achieve, then we do present efficient approximation algorithms, this one in subpolynomial time, and there's been previous work where this can be done in polynomial time in 1/epsilon. Actually, these other works also allow for non-translation invariant systems. In that case, it's also interesting to consider the runtime with system size, but that doesn't come up in our setting. In higher dimensions, there are proofs that it's computationally hard to determine the free energy as long as you're above some fixed finite temperature T1, so-called critical temperature, where the proof actually also just uses a classical system. So in higher dimensions, this computational problem is much harder. Nevertheless, as long as you are above another critical temperature, it must not be the same as the one in the proof of the hardness here. It's known that there are efficient approximation algorithms for the free energy. Again, polynomial runtime in the inverse error. If you look at this picture, there might also be some open questions. For example, if you can do this in subpolynomial time in 1/epsilon, can we actually achieve something even better? Could we get some runtime like log 1/epsilon as we could do in the classical case for computing the free energy in 1D? Or if we don't expect this to be true, I would probably not expect it to be true, then can we actually prove a hardness result on this computational task? Also, it's interesting that a similar picture like this one holds for other questions in many body physics. For example, like how do correlations behave in many body systems, or where occur phase transitions? And all these actually have a similar picture, that these things can occur in ground states of quantum systems or in higher dimensional quantum systems, but not in 1D and not at sufficiently high temperature. So it would be kind of interesting to look at how these questions are connected. With this, I'm about to conclude my talk, and thank you for your attention.